Good afternoon. From one important topic to another, right? We looked at a technique of circuit analysis, which is the node voltage analysis. We'll look at mesh current analysis now. There are some special cases where we can apply node voltage analysis, especially for dependent sources, also for super nodes. But I'm going to take that after we get done with mesh current analysis. Okay, so let's look at this. 113. All right, so voltage source and supernode, as I said, well, we'll come back to this after we get done with mesh current, so sometime next week, not today. All right, for now, let's look at mesh current analysis. So at the beginning of the chapter, we talked about identifying nodes, loops, branches, and meshes, right? So mesh is a simple electrical loop, meaning it does not contain any other loop inside of it. They're very easy to identify. Surface level on a planar circuit like this one. It's a loop that starts at one point, comes back to the same point, and it does not loop back on any cell, meaning it does not have any other loop inside it. In this circuit, we can identify that there are 1, 2, 3, 4, 5, and 6 loops. 6 electrical loops. But out of those 6, 3 of them contain other loops inside it. And so we only have 3 meshes. Mesh 1, mesh 2, and mesh 3. Right? Everybody understands the difference, right? A mesh is a simple loop, does not contain any other loop inside it. And based on that identification, we can apply a technique known as mesh current analysis. The goal of this technique is the same as the other techniques. We will derive and generate equations, linear equations for this linear circuit, and we would solve those equations to obtain values for unknown quantities. All right, so in mesh current analysis, the first thing we do is identify all the meshes. We assign a mesh current to each mesh. And here's the most important point. Mesh currents are not branch currents. Mesh currents are purely hypothetical. Or theoretical, if you will. They do not exist in real life. Let me write it on here. Let's keep it here. Okay, they do not exist in real life. They are purely hypothetical or theoretical. They're not real. That's the first thing. Then you assign a mesh current inside each mesh. Okay, the direction of the mesh current does not matter. It can be clockwise, it can be counterclockwise. It absolutely does not matter. As a force of habit that I've developed over the years, I always choose clockwise. Okay, so the direction does not matter. Direction can be clockwise or counterclockwise. It absolutely does not matter what direction you choose. Okay. Then we apply KVL and we sum up the voltages that are caused due to these mesh currents. In node voltage analysis, we assign a reference node and we express each voltage in terms of the node voltages. Here in mesh current analysis, we apply KVL to sum up all of the voltages. Okay. So if we look at these meshes, let's say mesh 1, for instance, what do we see in mesh 1? Mesh 1 consists of a voltage source, a resistor, another resistor, and you have one mesh current I1. Actually, you know what? Let me wipe this out and make this bigger. All right. M1 voltage source, resistor, another resistor, right? And then you have mesh current flowing through it in the clockwise direction. Now, if you, that's R2, and that's R3, and that's VA, right? And we have, let's see, we have mesh current I1 going through this. Also, this is a shared branch. So we have I2 flowing in this direction, and we also have I3 flowing in that direction. Okay. Now, each one of these mesh currents is going to cause a voltage drop, right? Current flows through a resistor, it causes a voltage drop. Hypothetical current flows through, causes a hypothetical voltage drop. So I'm going to mark out these voltage drops. Let's use okay. So let's say if I apply KVL, how many voltages do I have there? I have VA, then I have VR2, and I have VR3, and they should all sum up to 0. The way I apply KVL, I sum up the voltages in a clockwise direction. So I'm going to write minus VA plus VR2 plus VR3. Okay. But there's actually two voltage drops associated with both VR2 and VR3. So minus VA plus VR2 due to I1 and minus VR2 due to I3. VR3 again has two voltage drops, so it'd be VR3 due to I1 minus VR3 due to I2. And this would be equal to 0. Now let's take a pause while you write it all down and you think over this. While you're thinking, I'll just like to remind you, mesh currents, hypothetical mesh currents are hypothetical. They are not real. They do not exist. Hence, the two voltage drops that we see there are also hypothetical. They do not exist in real life. All right, any questions? If you have a preferred method of applying KVL, you can do so and you will still obtain the exact same equation. There would not be any difference. Okay. All right, so let's explain. The resistors R2 and R3 are in a shared branch, meaning that branch is shared between two meshes. R2 is shared between I1 and I3, sorry, M1 and M3, right? R2 is shared between these two, and R3 is shared between these two. Make sense? So we say there are two mesh currents flowing in both of those resistors. But voltage and current, by its very physical definition, by its very physical nature, cannot flow in two opposite directions. If a car is moving from left to right at the same time, you cannot say there's a car moving, the same car is moving right to left. Okay. Voltage, by its very definition, is the difference in electric potential between any 2 points. And I talked about this before also. So by its very definition, either one point must be higher than the other one. Either this right hand is higher than the left one or the left hand is higher. Right? They both cannot be at the same time. They're both at the exact same level. There is no difference in electric potential. Hence, there is no voltage between the two. Am I making sense? Right? So mesh currents, two mesh currents cannot flow in the same, two actual currents cannot flow in the opposite direction in any component. Not in a resistor. Okay? Not in a resistor. The current flows in a resistor because one end of a resistor is higher than the other. But mesh currents are not real. They are theoretical. They are hypothetical. And so this is the most important point here, that when we have a mesh current flowing to a resistor, it causes a voltage drop. If it is in a resistor that is not shared, like this one, R1 and R4 are not shared, then you only have one mesh current flowing through it. It only causes one voltage drop. But when you have a shared resistor and you have two mesh currents flowing through it, you have two voltage drops, and you must account for both of them in your KVL equation. So when you sum up the voltages, we obtain plus VR2 and minus VR2, plus VR3 and minus VR3. And of course, it depends on the direction of the current. If I choose all my currents to have a clockwise direction, then it is inevitable that one current will be flowing in the opposite direction to the other one. It is inevitable. If you choose all currents in clockwise, all currents in the counterclockwise direction, then the shared branch will have two opposite mesh currents flowing through it. So one will be added up, one will be subtracted. Does that make sense to everyone? Not the entire process, just these steps. Just these steps. Are these steps, did they make any sense? Again, hypothetical, yes. So a question being asked is, it's a good question. What if we assign one clockwise and one counterclockwise? Yes, then you have to take that into, instead of subtraction, it'll be a summation. And that's why I'm emphasizing this plus and this minus, is because they're in the opposite direction. So they cause a voltage drop in the opposite polarity. See, this positive is due to this current right here. And this, sorry, and this positive here is due to this current right here. If I2 was chosen as counterclockwise, then both the currents would be coming down from the top and both voltages would be positive. But the key thing to keep this in mind, we are only dealing with mesh 1 right now. When we get to mesh 2, we still observe the same direction of the mesh currents. We do not change them. Once we make an assumption, we do not change that assumption halfway through our problem. Meaning if we choose clockwise for all currents, it remains clockwise for all three meshes. Otherwise, our equations will not balance out. Otherwise, there'll be an error in our calculations. So once you make an assumption at the top of your analysis, at the top of your solution, you stick with it until the end of your solution. Okay, so now, because I have opposite directions, I have one positive, one negative voltage. And if I sum these up, I get minus VA plus I1 R2 minus I2 times R2 plus I1 R3 and minus I2 R3 is equal to 0. I can rearrange the terms and I can write I1 minus I2 times R2 plus I1 minus I2. Oh, wait, this is I3. Times R3 is equal to VA. At this point, you plug in all the known values. Your known values would be your resistor values and your source, which is VA. And you have generated equation 1. So reduce to AX plus or minus BY plus or minus CZ is equal to plus or minus D. A, B, C, D are constants. X, Y, Z are your variables or your mesh currents. Okay. All right, questions. All right, let's look at the second mesh. And for this one, I'll write the equation directly. All right, so you have R3, R4, and VB. Right, so M2 you have R3, R4, the direction of VB. Yeah, plus minus VB. This is R3. This is R4. Now, R4, of course, does not have any mesh through it. So I2, this is I1. This causes a voltage drop in this direction, plus minus, and this will be plus minus here. And this will also be plus minus. So if I write the KVL expression for this, I get VB plus VR4 plus VR3 is equal to 0. VB stays as it is, of course. VR4 would be I2 times R4, and VR3 would be I2 minus I1 times R3. After you write it down, take a look at the previous equation from mesh 1 and look at this equation, specifically the value for VR3. And tell me what you see. In the first one, what do you see? Very similar, but the only difference is, yep, because you're applying KVL in mesh 2 and not mesh 1. Now, going back to David's earlier question, if the current direction was chosen, let's say I1 was clockwise and I2 was counterclockwise, then let me write it down so that way. If I1 is clockwise and I2 is counterclockwise, then in mesh 1, VR3 would be equal to, any guesses? I1 plus I2 times R3. And in mesh 2, VR3 would be minus I2 minus I1 times R3. And that's why it does not matter what you choose as the direction for your mesh currents. Because when you write equations for all the meshes, your equations will always balance out. All right, pause and let me know if you have any questions. Any questions? Do the steps make sense? Do the explanations make sense? To further your understanding about this, I would suggest if you have a preferred method of applying KVL, you go through these steps with your own preferred method. Apply KVL clockwise, apply KVL counterclockwise. It does not matter how or which direction you choose for your mesh currents or how you choose to sum up the voltages. Your eventual equations will be exactly the same as these. They would not change. You have applied KVL, right? Previously in physics classes, also for this class. When you apply KVL, have you applied KVL to the same loop where you summed up the voltages in a clockwise direction and the counterclockwise direction? Have you ever tried that before? Do you think you would obtain a different equation? Answer is you would not. Doesn't matter how you sum up the voltages, the signs will remain the same. If you add up the voltages in one direction, your voltages might be positive. If you add it up in the other direction, they would be negative. The equation will remain the same. You're still summing it up. You're still following law of conservation of energy. Everything summed up should equal to 0, right? So you add up the voltages in a clockwise or a counterclockwise direction, it'll add up to 0. If you choose a different direction for your currents, that also does not matter because this equation will then be balanced out by this equation. Does that make sense? You had I1 plus I2 in the first one, and the next one you had minus I1 minus I2. And if you choose clockwise directions for both or counterclockwise, you will get I1 minus I2 for the first one, and the next one you get I2 minus I1. Okay. All right, questions before we move on to an example. I'm not going to do mesh 3 because when you get to an example, it'll make just the same thing. Any questions? Okay. All right. Let's move on then to example. Simply summation of the mesh current analysis. First step is assign mesh currents to every mesh. Choose a direction. Apply KVL and then apply Ohm's law. Okay, and then finally reduce each equation to a linear equation in the form of AX plus or minus BY plus or minus CZ, and then solve those linear equations. All right, calculators out, and let's solve this this problem. Okay, how many meshes do we see here? 2, right? Let's say this is M1 and this is M2 right here. Right, we don't need to pick a reference node in here. This is not node voltage analysis, so it doesn't really matter where ground is connected or where it's not connected. Okay, let's choose clockwise current directions for both. I'm going to choose I1. Actually, let me not choose I1 because I1, I2, I3 are already assigned as branch currents. So I'm going to choose a different subscript. I'm going to choose IX and IY. Again, does not matter what you choose. I Batman, Iron Man, whatever. But you want to keep it short, obviously. So let's choose, let me choose uppercase IX and IY. Okay, IX and IY. Apply KVL to mesh 1. How many voltages do we see? 3. 3 voltages in each mesh actually. So I'm going to write KVL according to the technique. Yeah, 100 volts plus 4 times IX plus 10 times IX minus IY is equal to 0. Therefore, 14 times IX minus 10 times IY is equal to 100. That correct? 4x, 10x, 14x minus 10 times IY is 100. Did you all obtain the same thing? I'm going to call that equation 1. Okay, that's equation 1. Then apply KVL to mesh 2. When we apply KVL to mesh 2, we obtain 4040 plus 10 times IY minus IX plus 5 times IY is equal to 0. And so I get minus 10 times IX plus 15 times IY is equal to minus 40. I'm going to flip it to the other side, so I get 10 times IX minus 15 times IY equal to 4040. This is equation number 2. Solve this, let me know what the answer is. If I take equation number 1, multiply it by 1.5, I obtain, what do I obtain? Right, 21 times IX minus 15 times IY, right, minus 21 plus 15 is equal to minus 150. This is equation number 3. Equation 2 plus 3 is going to give me, what does it give me? Minus 31 IX is equal to minus 190. Therefore, IX is equal to 90 divided by 31, 6.129. Is that correct? Someone solve it either on their calculators, online. What do you get? So let's see. What did you get? 10 for IX. Okay, so where did I go wrong? I went something wrong somewhere. I got minus 10x plus 15IY minus 40 times 1.5. So it's 14, 21 minus 1.5. So 15IY. 100 times 15 minus 150. Oh, I added the wrong equation. No, wait. 10x, 10 and 21. 31, 15. Oh, 40 and 150. There's where I went wrong. This is minus 110. That still doesn't give me the right answer. All right. I'll figure it out later. But you all solve the equation and you obtain Ix is equal to 10. Anyone else? I think I heard some nods there. 10. Okay. All right. Solve for Iy. How much is Iy? 4. So solve for I1, I2, and I3. What is I1? They are the 3 branch currents flowing through the resistor. We don't need to calculate. How much do you think it is? I1 is the mesh current Ix because there's only one current in there. And so it's 10 amps. I2 is simply equal to Iy, 4 amps. However, what is I3? Is it Ix minus Iy or is it Iy minus Ix? To answer that question, we look at the directions for all 3. So we look at the direction for the branch current, I3. Then we look at the directions for the mesh current. Now, if I3 direction was not given to us, then we would simply say, take the larger of the mesh currents and subtract it, and the larger mesh current would be the direction of the actual branch current. But the direction of I3 is given to us. So we have to assume that the mesh current that is flowing in that direction is the larger one and calculate based off that. In this case, Ix is 10 and Iy is 4. So it simply becomes 10 minus 4. But let's say I3 was given as going up instead of going down, meaning the problem statement itself is showing you that I3 is moving up. If that's the case, then you must calculate it as Iy minus Ix. Again, I3 is given as flowing in this direction. If this is given and Ix is coming down and Iy is going up, then I3 must be calculated as Ix minus Iy. If it was given that I3 is going up, then I3 would be Iy minus Ix. And we would obtain a negative value for I3, but that doesn't matter. Okay. So that's the little detail that you need to pay attention to. So if there's a problem that appears in a quiz or in the final exam with a direction already shown to you, you must keep that in mind. That is what is meant by when employers post a job and it says, looking for candidates who pay attention to detail. Okay. Did the process make sense? Any questions? Okay. All right. So we have about 9 minutes left. 9 minutes left. So what I'm going to do is, instead of going into this example now, let's see. Let's talk about supernode, but okay, let's just talk about supernode. All right. So in node voltage analysis, we apply KCL, right? We assign a branch current to a resistor and we apply KCL. However, what if we have more than one voltage source in a circuit and we are asked to solve with node voltage analysis? We cannot represent the current flowing through a voltage source in terms of its resistance, right? There's no way to do that. So what we do is we take the two ends of the source and we combine it into sort of a supernode. Now it sounds like a fantastical concept, but in reality, it's far more simpler and straightforward. All we are doing is we are assigning a empty current, not empty current, but a variable to that branch current that's flowing through that source. Let's say we call this Ix. Okay. So if you have a voltage source, we cannot express the current flowing to that source using Ohm's law. So we just assign a random current to it. Let's say it's Ix. Okay. And if that current is Ix, we apply KCL at either end of the voltage source. Don't know why I do that. And I start to the far right. And you apply KCL to both ends of the current source. Doesn't matter how many currents are entering or leaving. At one end of the source, you would obtain Ix equals to a something, something, something. At the other end of the source, you would expect Ix is equal to something. So you have two KCL equations at both ends of that voltage source. Right? So you have two KCL equations. The common thread is the voltage source current, which is Ix, is present in both equations. You rearrange the terms, so you obtain Ix is equal to A, and you obtain Ix is equal to B. Not necessarily a solution, but you'd have some KCL equation. And then you can simply write A equals B. Thus, we have no need of Ix. Ix is an unknown variable, but we wrote KCL expressions at both ends, both terminals, and we can combine it together. And we simply have an equation that does not account, that accounts for the current flowing to the voltage source, but it's not part of the equation. So we combine both ends of the voltage source together into a super node. That's all the concept of supernode is. You apply KCL, it's a shortcut to apply KCL at both ends of a voltage source. And that's all. This is useful only when you have more than one voltage source in a circuit. Okay, if it's one voltage source in a circuit, you simply take the negative end as your reference and you calculate based off that. But if you have two voltage sources, then obviously we can't do that. You can only have one reference node in a circuit. And once we choose that reference node, all the others must be calculated. So in this case, you have two voltage sources, and hence we need to apply KCL and create a supernode. A supernode is nothing but a shortcut. It allows us to skip two steps. The shortcut that allows us to skip these two steps. Ix is equal to A and Ix equal to B. That's all. So it allows you to apply KCL directly. All right. Any questions? Okay. All right. Lots to think about. We'll end class here today, and I'll see you all on Monday. Quiz on Monday based on node voltage analysis. I will not ask you anything about super nodes, the straightforward solution or solving of a circuit using the node voltage analysis problems. Okay. There's a homework that was that's due. But it's based on node voltage analysis. So please practice those problems. And you'll do fine on that quiz. Okay. All right. See you next week.